You asked me if an ordinary person, by studying hard, would get to be able to imagine these things like I imagine them. Of course, I was an ordinary person who studied hard. There's no miracle people. It just happens they got interested in this thing and they learned all this stuff. They're just people. There's no talent, a special miracle ability to understand quantum mechanics or a miracle ability to imagine electromagnetic fields that comes without practice and reading and learning and study. So if you say you take an ordinary person who's willing to devote a great deal of time and study and work and thinking and mathematics and time, then he's become a scientist. When we were talking about the atoms, one of the trouble that people have with the atoms is that they're so tiny and it's so hard to imagine the scale. That the size of the atoms are in size compared to an apple is the same scale as an apple is to the size of the earth. And that's a kind of a hard thing to take. And you have to go through all these things all the time. And people find these numbers inconceivable. And I do too. And the only thing you do is you just change your scale. I mean, you're just thinking of small balls, but you don't try to think of exactly how small they are too often, or you get kind of a bit nutty, all right? But in astronomy, you have the same thing in reverse, because the distances to these stars are so enormous. You know that light goes so fast that it only takes a few seconds to go to the moon and back, or it goes around the Earth 7.5 times in a second. And it goes for a year, 2 years, 3 years before it gets to the nearest other star that there is to us. But all our stars are in the stars that are nearby in a great galaxy, a big mass of stars, which is called a galaxy, a group. Well, our galaxy is, what is it, something 100,000 light years, like 100,000 years. And then there's another patch of stars. It takes 1 million years for the light to get here, going at this enormous rate. And you just go crazy trying to make too real that distance. You have to do everything in proportion. It's easy to say the galaxies are little patches of stars and they're 10 times as far apart as they are big. Well, that's an easy picture, nobody gets it. But you just go to a different scale, that's easier. And once in a while you try to come back to Earth's scale to discuss the galaxies. But it's kind of hard. The number of stars that we see at night is only about 5,000. But the number of stars in our galaxy, the telescopes have shown when you improve the instrument. We look at a galaxy, we look at the stars, and all the light that we see, the little tiny influence, spreads from the star over this enormous distance of 3 light years for the nearest star. On, this light from the star is spreading. The wavefronts are getting wider and wider, weaker and weaker, weaker and weaker, out into all of space, and finally the tiny fraction of it comes in 1 square, eighth of an inch, tiny little black hole, and does something to me, so I know it's there. Well, to know a little bit more about it, I'd rather gather a little more of this tiny fraction of this front of light. And so I make a big telescope, which is a kind of funnel that the light that comes over this big area, 200 inches across, is very carefully organized, so it's all concentrated back so it can go through a pupil. Actually, it's better to photograph it, or nowadays to use photocells, they're better instruments. But anyway, the idea of the telescope is to focus the light from a bigger area into a smaller area so that we can see things that are weaker, less light. And in that way, we find there's a very large number of stars in the galaxy. There's so many that if you tried to name them, 1 a second, naming all the stars in our galaxy, and I mean all the stars in the universe, just this galaxy here, it takes 3,000 years. And yet that's not a very big number. Because if those stars were to drop $1 bill on the Earth during a year, each star dropping $1 bill, they might take care of the deficit which is suggested for the budget of the United States. So you see what kind of numbers we have to deal with. At any rate, I think that the numbers are a problem in astronomy, the sizes and numbers, and the best thing to do is to relax and enjoy the tininess of us and the enormity of the rest of the universe. Of course, if you're feeling depressed by that, you can always look at it the other way and think of how big you are compared to the atoms and the parts of atoms, and then you're an enormous universe to those atoms, so you can sort of stand in the middle and enjoy everything both ways. But the great part of astronomy is the imagination that's been necessary to guess what kinds of structures, what kinds of things can be happening to produce the light and the effects of the light and so on of the stars that we do see. And I could take an example, an historical example. See it many times in science. By using imagination, you've imagined something which could be, according to all the known knowledge of the laws, and you don't know whether it is yet or not. And that's very interesting. There's a creative imagination, you'd like to call it, not just imagining things that are relatively easy, but something different. And to take an example of a star, as we understand it, the ordinary star like the sun is a great big ball of gas, of hydrogen. It's burning up the hydrogen and so forth, and it's an enormous mass of gas. And it's held together by gravity. You don't have to always understand gravity as curved space. It's good enough for this purpose that force inversely is square of the distance. When things are closer together, the force is stronger. And it pulls everything together. By the way, that's why the world is round. Because the globe of Earth is pulled together as much as possible. And if it had a great mountain and an irregularity of a bump or something, it would be pulled in by gravity and it all gets smooth. Rocks aren't strong enough to hold a bump much bigger than a few miles, and Mount Everest is our biggest bump. But on the moon, where the gravity's less, the bumps are higher, the mountains are bigger on the moon. Anyway, to get back to the star, it's all held together by gravity, and it's got a nuclear fuel, which we haven't been talking about, that's burning up the hydrogen and generating energy, which keeps things going. And after a while, it would use the fuel up. And people began to think about what would happen then. And it would be possible to just be gas sort of hanging around, held together by gravity, but quiet. But another possibility was to think, if I push the stuff together closer, the gravity is stronger. Would it hold together? Well, if you push a little bit together, the pressure increases. When you push gas together, there are more atoms and they pound harder, so the pressure's higher, but the gravity's stronger. And it turns out the pressure wins, so it would just come out again. If you push a star in like that, it oscillates. And there are some stars that are oscillating and vibrating and so on, but it turns out if you keep on analyzing it and you push it together very far to the incredible concentration that the whole mass of the sun is down to the size of the Earth or smaller, then it turns out all the nuclear matter, all the nuclei of the atoms are all stuck next to each other tight. The electrons are, spaces where the electrons are, is all squashed out, and it comes out that when you get to that far, the gravity's strong enough, has overpowered the pressure again. Even though the pressure's got to be enormous, the gravity's got to be even more enormous, and the thing will stay steady at a different size and be nothing but a neutron's nuclear matter, nothing solid nuclear matter. And this is a possibility was worked out by Oppenheimer and Volkoff, and it's called a neutron star. And people waited to see if there were any such neutron stars for years, until recently they found these strange pulsars which emit flashes of radio waves, and later they found light, which can go 30 times a second, for instance, the fastest ones, or maybe 10 times a second, or 1 a second. And at first, that's very mysterious. You're used to stars being big and slow, and how can anything in a star move in a 30th of a second? Well, these things are very small neutron stars, and they're spinning very fast. And there's some, for reasons not yet understood, they're emitting a beam of radio waves, like a searchlight in an airport or something. Those things that go around, boop, boop, boop. So we get the flashes, tick, 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 that fast. To imagine a star the mass of the sun doing something, turning so fast as 30 times a second is another one of these big number, hard to conceive imaginary things, okay? And the whole idea that there could be a star of such enormous density that a teaspoon would weigh so much that of the matter that if you put it down on the Earth's surface, it's so heavy it'll just plow right through to the center of the Earth, and things like that. It took a lot of imagination. It comes out of the mathematics and the analysis and all this that help you to make sure you're not making a mistake. And it turns out that such a star was possible, and it turned out later, in fact, they do exist. And that's a good example of how imagination is a useful thing and produces a guessing ahead of time, and how we make advances by using it. Besides just the very difficult thing of imagining all the things that might be up there to explain the things we see. In the case of astronomy, we have a large number of things that we see that we are not yet quite clearly got the imagination to see what it is that's producing it. Quasars are very powerful sources of light and radio waves for very great distances. We can see them because they're so bright. And the exact cause of their sources is only gradually being recently understood in terms of another nutty concept of imagination, the black hole, which is something that comes from following the logic of the gravity theory of Einstein to its ultimate, working out the consequences in crazy circumstances. Suppose you had an amount of matter so great that the gravity force is so much that even light trying to get out falls back. Nothing can go faster than light, and nothing could escape. You couldn't see it. Well, how would you get there? If you had a lot of matter to start with, it could fall together and get into this condition that no longer could the light come out. And so you would have this thing which would continue to attract things to it. Things would go in and nothing would come out. That's called a black hole. And you say, well, how can a black hole, which is absorbing everything, make all this energy that we see? Is that an explanation of the quasar? Actually, it may well be, because if the things are falling in don't go plunk in, but go around, falling in by swirling, then as they fall in and irregularly and so forth, and in the fast motions that it produces, they go down this whirlpool, they generate a lot of energy and friction and so forth, and different kinds of effects, magnetic and electric effects, that could make the jets of matter that come out of the quasar and the radio galaxies in ways that are not really understood. We don't have a real picture of why there are jets of radio waves and so matter emitting radio waves in galaxies. There are galaxies in which great jets have come out of big clouds of matter on each side, which are emitting radio waves. So there's some kind of a source in there that sort of gets wound up and shoots these jets of material out with tremendous energy, and it's guessed that maybe that's a black hole somehow or other. And the somehow or other is the challenge of imagination, which has not yet been answered by anybody with any great confidence.